Good afternoon, everyone. I'm Lise Deschutter, and I'm working at Lille University, and I will present my work about optical properties of copy dust and its pure compound. And this work has been done at the PC2A laboratory and in the LOA laboratory. So first, let's focus about the optical properties of aerosol. So the atmosphere can be recorded using remote sensing and especially from satellite observation. With onboard spectrometer on satellite, it's possible to record gas and aerosol at the same time over a global scale. An example here, where we have a spectrum with the clear sky and a spectrum with the aerosol contribution. So there is a difference. So it could be nice that from this information, we can have the size of the particle, its concentration, and its chemical composition. But for that, we need an important physical parameter, which is the complex refractive index. Once we have this parameter, it could be possible to identify the different sources of aerosol over the globe and understand the transport of the aerosol and maybe get more information about how the chemical composition evolves during transport. So first we have to determine the complex refractive index. So there is two ways. First, we directly determine the Cree of the sample, and this methodology has been already done in our team. We use a sample like collected sample or commercialized sample. We don't need any information about the chemical composition, but it only provides the refractive index of one specific sample, which is not giving a global information of the natural sample. The other way is to use effective medium approximation. It says that complex refractive index of a mixture can be calculated based on the complex refractive index of pure compound and their volume fraction inside the mixture. But in that case, we need to know the refractive index of the pure compound and their volume fraction in the natural sample. But in the literature, there is still limitation about the database of the refractive index of pure compound. They are often done with a low spectral resolution, with a narrow spectral range or only a specific spectral range, and on bulk material or press pellet, which is not representative to particle in suspension. So in our team, we will combine both of these ways. So first, we will directly determine the refractive index of our case study sample and its pure compound, and we will test some mixing rule of the Cree of the pure compound and compare it with the refractive index we obtained here on our case study sample. So let's have a look about the methodology. So first, we generate the aerosol. So the aerosol as a powder is in a reactor put back in suspension using magnetic steering and a nitrogen flow. Then we will characterize the aerosol using spectrometers to get extinction spectra over infrared and UV visible range, which is important to interpret the satellite recording. And we will also measure the size distribution and apply then an inversion algorithm using MIFARE, continuous distribution of ellipsoid approach when it's necessary, the case for non-clay material, the Kramers-Kronig relation, and an optimal estimation method to get at the end the refractive index at each wave number. Let's see about the experimental setup. So we retrieve here the generation of the aerosol, we retrieve here the characterization of the aerosol. So it's combining a Fourier transform spectrometers with a UV visible spectrometers, which allows to have a spectral range from 650 centimeters minus 1 to 40,000 centimeters minus 1, with a resolution which could go until 0.5 centimeters minus 1, which corresponds to the one that Yazi spectrometers use to record the atmosphere. And at the end, we have a size distribution measurement combining APS with SMPS to get a wide diameter range. Now, we will explain why we had to use an inversion process. So at the beginning, the input is the extension spectra. So we can get from the extension spectra, we can get the extension coefficient, and this extension coefficient can be also calculated using mean theory. So it will be then possible to isolate the Cree of the compound, but if you remember, the Cree has two parameters, the real and the imaginary refractive index. So it's two unknowns and one equation. So we have a mathematical problems. That's why we will apply an inversion algorithm. So as an input, we use experimental extinction spectra. First, a priori, we say that the extinction coefficient is equal to kappa, the imaginary part of the refractive index. Then using Kramer-Kronig, which express the real part as function as the imaginary part, we can get the real one, so n. So we have couple of n and kappa, and we can calculate with the mean theory and calculated extinction spectra. So we get extinction coefficient using this equation and the size distribution. And then we will optimize the couple n and kappa with minimization between the calculated extinction coefficient and the measured one using an OEM, correcting the kappa, and after doing a loop until the minimization is done, and at the end we retrieve the refractive index. So let's focus about our case study. So our case study is mineral dust from Gobi Desert. So why we choose mineral dust? Because mineral dust is one of the major sources of aerosol in the atmosphere. And why Gobi? As you can see above, Gobi was really interesting because it has a complex chemical composition. So our sample is coming from the EMT, and as you can see, the chemical composition, we have halite, quartz, and calcite, which are the main pure compound inside Gobi. And we found also this in other work in literature. So next, we will apply the methodology I presented previously on Gobi and its three main compounds, halite, quartz, and calcite. So let's see some results. So first I will present the extinction spectra of the pure compound and Gobi. So here you have the extinction spectra. Here the size distribution measured with the parameters. So here the infrared, the UV. In the infrared you can see the main absorption band, here corresponding to silicium oxide stretching and bending. And here you can see the diffusion slope. We have the same for quartz, but here it's different. We have a double peak. It's because quartz is a crystalline compound, non-clay material, and in that case there is ordinary and extraordinary that overlap, so that's why we see these double bond structures. Extension spectra of calcite. So here it's also a non-clay material which is crystalline also, but in that case the ordinary and extraordinary rays are separate, so we can distinctly see them. And here, if you can see in the diffusion slope, we have some harmonics corresponding to the main absorption band. This could be really interesting also to retrieve them in the complex refractive index and see them in Gobi. Why not? So here the Gobi extinction spectra, and then we will try to see if all these features correspond to the main three compounds. After the extinction spectra, applying the inversion algorithm, we apply the Cree of the pure compound. So here it's the case of halite. So we retrieve the refractive index over the whole spectral range. And as you can see, there is difference with the literature. And in that case, for halite, I had to combine three different works, three different set of N and kappa. And as you can see, for example, here in dot line and after here the black line, which is two different works in the literature, they are not homogeneous between them. Kramer-Kronig is not applicable. So here we give a new things to the literature that we have homogeneous complex refractive index over this whole spectral range. If we look now at quartz, we can find out again the same features, the double peak, the small peak here. For example, for you to know, in the literature, the refractiveness of quartz doesn't give these two peaks. So there's this one, but less resolved. We don't see the double peak. And this one is not seen because of the resolution. Here we have a better one, so we are able to see this small peak. And in the calcite, as we said, the harmonics, we can retrieve it at the end on the complex refractive index. And finally, the refractive index of Gobi. So we will check now if it's possible to explain the extinction spectra we saw before and this Cree of Gobi with the Cree and extinction of the pure compound. So let's first focus on the extinction spectra. So we will try to identify the pure compound. So here you have Gobi, the main one in gray. And here you have all the extinction spectra of the pure compound. So here you have the green one, which is highlight. So we can identify in Gobi highlight. We can identify calcite. And in that part, we can also identify quartz. We do a zoom, this double peak, and also again calcite with this peak. So it seems to work for the extinction spectra. Let's have a look on the complex refractive index. So I choose to only look at the imaginary part. So here we have Gobi again. And it seems also that we can explain also the kappa of Gobi with the different kappa of the pure compound. Also this feature of quartz, which is also here, and the double peak here. So it's possible to explain the optical properties of Gobi using the three main compounds we choose. But the only problem is that the spectrum I show you, it was normalized. So I modified the concentration or the intensity with an empirical factor in order to fit and to better see where the pure compound are fitting the features of Gobi. But it could be nice to now check with the real chemical composition and the real factor volumic fraction, for example, if it's possible to retrieve the refractive index of Gobi using these three main compounds. And for that, we will check some effective medium approximation. So there is different one, which links the optical data with the chemical composition. So there is the volume mixing approximation, which calculates an effective Cree thanks to the Cree of the pure compound and their volumic fraction. But this one, we are not sure that it will be possible to apply it because actually we don't have separate particle of each pure compound, but mix of compound inside a particle. So that's why we'll try these two effective medium approximation. They are determining the dielectric constant of the sample. And here there is two different ones, so we will have to test. And this is depending on the microstructure of the sample, how the compound are dispersed in the sample. So we'll try later this. As a summary, so we said at the beginning that it was really important to get a new methodology to improve the refractive index database, to get better information for satellite observation. For that, we developed experimental setup on response-bonded particle. We measure extinction spectra over a wide spectral range with high resolution, and we measure also at the same time the size distribution. Our algorithm is working. We retrieved the complex refractive index, and we had to use sometimes the CDE instead of me to retrieve the complex refractive index. And we apply that on Gobi dust and its three main compounds. And then we also saw that it's possible to explain the extinction spectra and the complex refractive index of Gobi using these three compounds. Some perspectives. So the question will be now, does this missing rule of complex refractive index present in the literature can be applied to natural samples? So we will apply this combination present in the literature and validate or not the principle, if it's possible to use this theory or not to retrieve refractive index of Gobi. Maybe we will need to get to know which rules to use. It will be maybe important to get more information about the chemical composition and the microstructure of the sample. And maybe use also the refractive index of other pure compound, because we use only the three main, but there is others, so maybe. And finally, the last question will be, could it be applied to satellite observation of Gobi particles during dust storm? So in another team, so that we are in partnership at the LOA, the PhD students use my extinction spectra of each pure compound in order to interpret the spectra of Gobi schistose from YASI data, and in order to follow the chemical composition of the dust, Gobi dust, as function as the position of the time during the dust storm. So it could be interesting to continue now with the refractive index and not only the extinction spectra. Thank you a lot for your attention, and I will be pleased to reply to some of your questions. Thank you.